Welcome viewers back to this course. So, today we are going to discuss the lecture number 8. In the last lecture we have discussed that how we can factorize the given second order linear differential equation with the help of Riccati equation, and then we have discussed that the Euler-Cauchy form. So, today we are going to discuss the next part, and that is now I just wants to move further, and I want to solve the differential equation, a general differential equation that is linear second order of the form a naught x y double dash plus a1 x y dash plus a2 x y is equal to some function f x. And this equation I just give it name 1, and I know that this can be further written as y double dash plus a1 x over a naught x y dash plus a2 x y is equal to sum f x over a naught x, provided that my a naught x, a1 x and a2 x are continuous function for x belongs to the interval. That interval we are taking is alpha beta. So, alpha beta. Then we can further write this equation as y double dash plus some function p x y dash plus q x y is equal to sum g x. So, this equation I know that is in the standard form. Now, so I know that if I am able to solve, so in this case this is also taken that my a naught x is never equal to be 0. Okay. So, my main purpose is now to solve the equation a naught x y double dash plus a1 x y dash plus a2 x y is equal to 0. So, this is the homogeneous part I want to solve, because but in the I know that this homogeneous part, that is equation number 2, can be solved using the help of factorization, and then we reduce it to the Riccati equation, and once I know the solution of the Riccati equation, then we can find out the solution of this equation number 2. But you know that the Riccati equation is a highly nonlinear equation. So, sometimes we are unable to find the solution for the Riccati equation. So, if we are unable to solve the Riccati equation, we cannot solve the given equation number 2 in this case, and other equation we are able to solve only is the Euler-Cauchy form. So, what will happen if we have a differential equation which is not of this form, either the Euler form, and neither I can find out the Euler-Cauchy form, nor I am able to find the solution for the corresponding Riccati equation. So, in that case, how I can solve this differential equation? And if you see that in the starting we have discussed that a differential equation in this case is a y solution multiplied by some function of x plus the derivative of that function, and then multiply by another function of x, and second derivative of the function plus another function of x. So, in this case we are multiplying the solution and all its derivative with some function of x. So, let us then this comes to our mind that because this is happen only if consider that, let me guess that my y x is a polynomial. So, I just write is as a C0 plus C1x plus C2x square, C3x cube and so on. And in this case I do not know that whether my this polynomial is of finite degree or infinite degree, because in this case if it is of finite degree, suppose I take this as a degree of 10. So, in that case what will happen, if I take the derivative, one derivative its degree will reduce to 9 and second derivative it will reduce to 8. Then a0x and a1x, depending on the values of these functions, we will be able to get the solution for the equation number 2 or not. Okay. So, in this case we can expect that this polynomial may be of finite degree or it will be infinite. So, now this one can be written as, I can write as a n is from 1 to infinity, from 0 to infinity Cn x raised to power n. So, let my solution is this one. Okay. And then I take the derivative of this polynomial or the series, we call it series also, y dash x. So, in this case it will be n Cn x raised to power n minus 1. So, in this case I have the n and n equal to 0 does not contribute anything in this series. So, I will take it from 1 to infinity, because when the polynomial, this is a polynomial in x, and if it has a infinite terms, then I can call this as a series also. I will just take further derivative, second derivative, and in that case I will get n minus 1 Cn x raised to power n minus 2. So, in this case n equal to 0 will does not make any sense, n equal to 1 does not contribute. So, it will start from n is equal to 2. So, I can write from here that n is equal to 2 to infinity. So, suppose I substitute all this one in the equation number 2. So, on substitution in equation 2, I will get, so from here I will get my A0 summation n from 2 to infinity n minus 1 Cn x n minus 2 plus a1x summation n from 1 to infinity n Cn x power n minus 1 plus a2x summation Cn x n from 0 to infinity equal to 0. Now, I do not know that what is the function a0x, a1x or a2x, because it may be the function of x also, it may be the constant also. So, depending upon that what is the value of this a0, a1, a2x, then we further can solve this differential equation with the help of this series, and then we can find the solution for this equation. So, let us take one example and try to find out that how this series solution can be useful to finding the solution of the equation. So, I will just take a very simple example. Suppose I take a differential equation y double dash minus 2x y dash minus 2y equal to 0. So, in this case this differential equation has constant coefficient here, constant here, but here it is a function of x. So, I do not know that how to solve this type of differential equation. So, then we substitute that, let my yx, because I consider that y may be the solution, may be the polynomial of infinite degree, so that is the solution of this equation. So, I will consider that let yx is the solution n from 0 to infinity Cn xn, and then I can take the derivative of this one. So, from here my equation, this equation I can call it number 3. So, this can be written as summation n from 2 to infinity n minus 1 Cn x n minus 2 minus summation 2x n Cn x n minus 1 n from 1 to infinity minus 2 summation n from 0 to infinity Cn xn equal to 0. So, I just substituted that whatever we got after taking the derivative, and then I will go further. This x I can take from here. So, this one equation becomes n from 2 to infinity n minus 2. So, this x will multiply by this. So, it will reduce to in this form. So, I will get n from 1 to infinity n Cn 2 times x power n minus summation n from 0 to infinity to Cn xn to Cn xn equal to 0. Now, in this case, if you see that here it is x raised to power n, it is also x raised to power n, but here it is x raised to power n minus 2. So, first thing is that we have to make the power of x same form in all the terms. So, this is the first term we want to solve. So, in this case I want to change this one into this form. So, what I will do that here I am putting n minus 2 is equal to m, some m I am putting. So, from here I will get n is equal to m plus 2. So, this factor the first term, this will reduce to, now if n is starting from 2, m will start from 0. So, from here I can write that m is starting from 0 to infinity, n is m. So, I can write it as m plus 2, it will becomes m plus 1, c it becomes n plus 2, and this becomes m x raised to power m. And then further, so this is the same thing, same equation. So, we can write this as n is equal to 1 to infinity 2n Cn n from 0 to infinity to Cn xn equal to 0. Now, this is the m, this is just the indices. So, index we can change as, so this equation after putting this one, I can change my m to n back, and then I can write this equation again as in the form of n. So, I can further make it as a n, it becomes n plus 2, it becomes n plus 1, and this become c n plus 2 and x raised to power n. So, now I have the same power x raised to power n in all the terms of the equation. So, which now the only thing is that, so in this case the first term the n is starting from 0, in the second term n is starting from 1, and in the third term it is starting from 0. So, I will write the equations corresponding to n equal to 0 first. So, if I put n equal to 0, I will get from here 1 into 2 c 2 x. So, n 0, so it is a constant, n will 0 coming from here also. So, this will be 2 c 0. So, this is the terms corresponding to n equal to 0, and then if I start from n is equal to 1, I can take all the terms together. So, it will become n plus 1, n plus 2, C n plus 2 minus 2n, from here I am writing 2n, Cn minus 2 Cn x raised to power n equal to 0. Okay. So, from here this one. Now, from here what we do is that now this whole series is equal to the 0. Then what we do to find out the coefficients, all the coefficient we equate the similar power of x equal to 0, and then we will try to find all the coefficients. So, once I equate the first term corresponding to n is equal to 0. So, that equation we have to equate, EQ equate. Equate the first term. So, from here I will get that 2 C2 minus 2 C0, and that is equal to 0. So, from here I will get my C2 is equal to C0. So, I get my coefficient C2 in the form of C0. Now, I can, instead of equating each term, what I can do, that I can put or equate the x raised to power n, coefficient of x raised to power n equal to 0, because here we are able to take the we are able to collect all the terms corresponding to the coefficient x raised to power n. So, if I what I do that, I will equate the coefficient of x raised to power n equal to 0 on both sides. So, from here I will get n plus 1, n plus 2 C, n plus 2 minus, so this is my 2n and this is my 2. So, from here I can write as minus 2 n plus 1 Cn equal to 0, which further can be reduced to this. From here I can write my Cn plus 2 is equal to 2 n plus 1, and then I can divide by this factor n plus 2 Cn. So, from here further I can write it as, so this will cancel out. So, I will get C I will get C n plus 2 is equal to 2 times divided by n plus 2 Cn, where n is starting from 1. So, that is greater than or equal to 1. So, from here I will get this relation in which if I know the value of Cn, I can find the value of Cn plus 2. So, this type of equation is called the recurrence relation. So, in the recurrence relation, if I know one coefficient, I can write the another coefficient in the form of that coefficient. So, I know that my C0 is equal to C2. So, for n is equal to 1, I can write my C3 as 2 over, so this is n equal to 1, so this will be 3 C1. Next, for n is equal to 2, I will get C4 is equal to 2 times, it is 4 C2, but C2 I know that that is also equal to C0. So, from here I can write as 2 by 4 C0. Then n is equal to 3, I will get C5 is equal to 2 by 5 C3, but C3 is given to me in the form of C1. So, from here I can write 2 by 5 multiplied by 2 by 3 C1. Then I can find out for n is equal to 4. So, it will be C6 will be 2 divided by 6 C4, and C4 is given in the form of C0. So, from here I can write by 2 by 6 into 2 by 4 C0. So, in this way I can find all this one coefficient. For the odd power I will get the coefficient in terms of C1, and for the even n will get the coefficient, all the coefficient in terms of C0. So, once I able to write this one, that I am able to find out the solution in this form, then from here I can write my solution Yx. So, Yx is C0 plus C1x plus C2 is already C0. So, I can write it as C0 x square. Then C3. So, C3 I know that is in the form of C1. So, I can write it here 2 by 3 C1 x cube. Then C4 in terms of C0. So, I can write it as a 2 by 4 C0 x raised to power 4. Now, C5 is also in terms of C1. So, I can write it as a 4 by 15 C1 x raised to power 5, and then further I can write as a C6, it will be 4 by 24 C0 x6 and so on. Now, from here I can solve further, and I will collect the term corresponding to the coefficient C0 and C1. So, if I collect the terms corresponding to C0, I will get 1 plus x square. So, this is x square plus 2 by 4 x power 4 plus 2 4 by 24 x raised to power 6 and so on, plus I then take the terms collecting the terms corresponding to C1. So, this will be x plus 2 by 3 x cube plus 4 by 15 x 5 and so on. So, in this case I will get the solution Yx. So, Yx is a general solution of the equation. So, if I once I know the general solution of the equation, then I can write this as Yx is equal to, now C0 and C1 are the arbitrary constants. So, I can write it as a C0 and then I will consider this as a function, that is y1x plus C1 and that is y2x. So, this is the general solution that we know, that contains two arbitrary constant, and that constant I can take as a C0 and C1, and this is I consider as this is y1x is a one solution and y2x is another solution. So, this one is the general solution if the question is that y1x and y2x are linearly independent, because here it is just a infinite series and here also it is a infinite series, and I want to check that whether this series infinite series and this infinite series are linearly independent or not. So, how we can verify or check whether these two functions y1x and y2x are linearly independent or not? Then we go further, go back to that Wronskians, and I know that the Wronskian, the corresponding Wronskian corresponding to y1 and y2x y 2x this can be written as w x. So, this I know that I can write y 1 x, y 2 x, and this is y 1 dash x, and this is y 2 dash x. So, I will try to find the Wronskians for this corresponding solution. So, from here I can write this Wronskian as 1 plus x square plus 2 by 4 x power 4 plus 4 by 24 x power 6 and so on, and x y 2 is this one. So, this I will take as x plus 2 by 3 x cube plus 4 by 15 x 5 and so on. Then I am taking the derivative of this one. So, this will be 2x plus 4 will cancel out, it will be 2x cube plus, so 6 will cancel out. So, it will be x 5 and so on, and this will be 1 plus 3 will cancel out, it will be 2x square, 5 will cancel out, it will be 20 by 15 x power 4 and so on. Now, if I want to take the determinant of this matrix, then it is very difficult, because if I take the derivative of this one, so this polynomial and this polynomial will be multiplied minus the multiplication of this polynomial. But here we are going to use the concept of the Wronskian. So, in Wronskians at one point that we have discussed in the previous lectures. So, now let I take x naught is equal to 0 and I try to find the Wronskian at x naught. So, if I take the value x naught equal to 0 and try to find the Wronskian here, so it will reduce to 1, 0, 0, 1, just putting x equal to 0 in the given given polynomials, and this value will be 1, which is never 0. And we know from the previous lectures that, so in this case my Wronskian at x 0 is equal to 0 is 1, and from my previous knowledge of Wronskian I can say that this Wronskian is never 0 for all value of x. So, once if I know that the Wronskian is never 0 for all value of x, so from here I can say that my solution, that y 1 x and y 2 x are linearly independent. So, if they are the linearly independent solution, then we can say that that is the general solution. So, in this case you have seen that the solution y 1 x and y 2 x are the polynomials of not a finite degree. So, this I can say that from here I can say that my infinite series, that my yx is C0 plus C0 y1x plus C1 y2x, and this is in a series, infinite series for that one. So, from here I can start a new concept, that a solution of the form of power series. So, this we call it as a power series solution. So, from here I can say that an infinite series of a function yx is equal to C0 plus C1x minus x naught plus C2 x minus x naught square, C3 x minus x naught cube, and so on. So, this one I can write as Cn x minus x naught power n is equal to from 0 to infinity. So, from 0 to infinity, this is called the power series of the function yx about x equal to x naught. So, this is the power series of function yx about the a point that is x naught. So, this is the power series of the function yx about the point x equal to x naught. And then so, this is the power series of this one, and so yx is C0 plus C1. So, that is already there. Now, I want to find what is the value of C0, C1, C2, C3. So, because these are the coefficients and the constants, and that we need to find with the help of yx. So, let us suppose I want to find my C0. So, what I do is that I just take it, give the name 4. So, suppose I want to find the value of C0, because this function has a power series, this one on the right hand side. I will try to find the value of the y at x naught. So, if you see the value at the x naught, all these terms will become 0, and from here I will get my C0. Further, I can, if I want to find the value of C1, what I do is that differentiate equation 4 with respect to x. So, what I will get? I will get y dash x is equal to C1. So, from here I will get C1 only, and then from here to C2 x minus x naught plus 3 C3 x minus x naught square, and so on. Now, what I do is that putting x equal to x naught, now putting x is equal to x naught, I will get y dash at x naught is equal to C1. So, from here I am able to find the value of C1, from here I am able to find the value of C0, and if you move further, then to find the value of C2, I will take differentiation, one more differentiation of this equation, and then I will get the value of C2, C3, and so on. So, if you from here you see that I can write my equation as yx is equal to summation n from 0 to infinity, and the Cn is, in this case it is just yx naught, it is y dash x naught. So, from here I can write that my it will be nth derivative at x naught divided by n factorial, and this will be x minus x naught power n. So, if we take the help of the function and all its derivative to find the coefficients, then the coefficients will be this form, and in that sense I will say that yx has Taylor series about point x is equal to x naught. So, in that case I can say that this power series become the Taylor series. So, now there are some properties of power series. The first thing is that I know that function yx has the power series, that is C0, C1x, C2x square, and C0 plus C1 x minus x naught plus C2 x minus x naught square, and so on. So, first thing is that I want to find out that how I can check that this is a convergent or not. So, in that case I will apply the Cauchy ratio test to find out that what will be if the series is convergent, what will be the radius of convergence of that series. So, in this case I will apply the Cauchy ratio test. So, in the Cauchy ratio test I want to find, I will take C. So, if this series is can be written as summation un x minus un n from 0 to infinity, then I know that with the help of ratio test, it will be un plus 1 over un. So, from here I can write it will be C n plus 1 x minus x naught n plus 1 divided by C n x minus x naught modulus value, because we know that the ratio test we can apply only for the positive values. So, in this case I am taking the absolute value. So, that will become C n plus 1 over C n. So, this is the ratio of the coefficient, and this will becomes x minus x naught power 1. So, this one. So, now we assume that let limit n tends to infinity, C n plus 1 over C n becomes lambda. So, this is a convergent series of coefficient and its value is equal to lambda. So, from here for convergence of the series, in that case my value, this will be lambda x minus x naught less than 1, because I know that if ratio is less than or equal to 1 as n tends to infinity, then it will be convergent. So, from here I can say that my x minus x naught will be less than 1 over lambda. So, this is called, this factor I call it as R. So, I can say that x minus x naught, x minus x naught modulus value is less than R. So, this R is called radius of convergence, and so this is called the radius of convergence of this power series, and this x minus x naught, the whole value is called the interval of convergence of the power series, and I can say that x in the region x minus x naught is greater than R, then the series will be divergent. Then, so this is the radius of convergence we have found. Then the next property is that the power series can be differentiated and integrated term by term, and the resultant series have the same interval of convergence. because whenever we take the power series of function, then it can be differentiated termwise terms and it can be integrated termwise terms, and the resultant series will have the same interval of convergence. Next is that the product of two power series, for example, I have a series, two series, and from 0 to infinity Cn x minus x naught power n and summation n from 0 to infinity dn x minus x naught power n. So, this is the two series I am taking. Then the product of the two series is again a power series, of the form n from 0 to infinity En x minus x naught power n, with the En term will be C0 dn plus C1 dn minus 1 and so on plus Cn d0. I will multiply the coefficients. So, that will be again the power series. And the next one is that the quotient that is Cn x minus x naught power n divided by dn x minus x naught power n is again a power series provided d0 is never equal to 0. So, if I take the ratio of the two power series, then it again a power series with d naught is not equal to 0. Next is that now after doing this one, we will try to give a new concept that is called analytic functions. So, what is the meaning of the analytic function? So, if a function f(x) can be expanded as a power series about a point that is x is equal to x naught. So, that we can write that my function f(x) can be written as summation n from 0 to infinity Cn x minus x naught power n, where my Cn is the nth derivative at x naught divided by n factorial. Then the function f(x) is said to be an analytic function. Okay. Then it is said to be an analytic function, because in this case we know that this function and all its derivatives exist, because we are able to find the coefficient Cn's only when with the help of the derivatives. As we have seen that I can find the C0 by putting the value of x equal to x naught in the equation, then C1 I can put taking the derivative C2 the next derivative. So, in this case my function f(x) is said to be analytical. In another form I can say that it is said to be an analytic function if all its derivative exists at the point x equal to x naught. So, this is the definition of the analytic function. Now, one theorem we want to discuss, that let the variable. So, in this case you can see that this function is a real valued function. It is defined on the x and it is a real valued function. So, let the variable x assumes complex values and let z naught be the point close to point x naught at which function f(x) or one of its derivatives fails to exist, then what do? You just compute the distance r in the complex plane, distance in the complex number z naught and x naught. Then the corresponding Taylor series of f(x) converges about x naught in the region in the interval x minus x naught less than r, and diverges for x minus x naught is greater than r. So, in this case, that suppose we are, what we have done, that we have the power series, and in that power series suppose that at some value of the x equal to x naught or some complex number, the function f(x) is fails or all its derivative fails, then the given power series has the convergence in this region, and it will diverge for the region x minus x naught greater than r. Okay. So, one more theorem, it will be useful for the definition. Let the function a1x over a naught x and a2x over a naught x have convergence as convergent as convergent Taylor series expansion about x is equal to x naught for the region x minus x naught a less than r, then every solution yx, then every solution yx of the differential equation a naught x y double dash plus a1x y dash plus a naught x a2x y is equal to 0 is analytic at x equal to x naught and radius of convergence of its Taylor series expansion about x equal to x naught is at least s, at least r. So, if this theorem says that if this, because in this case if I divide by a naught x, so if a1x a naught x and a2x divided by a naught x have the convergent Taylor expansion about x equal to x naught and the radius of convergence is r, then the average solution of the differential equation yx is analytic at x equal to x naught and the radius of convergence will be at least r. So, that is the lecture number 8. So, thanks for viewing this. Today in the class we have discussed that how instead of solving the instead of having the exponential solution, how we can have the solution that is a infinite series for the given differential equation. So, in the next class we will go further about the series solution. Thank you very much.